represent a defective bridge. So there is that aspect of the work that we will also talk about. There has been very limited work in essentially implementing this concept in practice. Now, having said that, there has been some work where you would build a numerical model, or essentially a model-based approach for drive-by damage identification, where you would build a digital representation of your asset, and you would have a very complex train bridge interaction model. And because this bridge ideally is calibrated against your site measurements, you also have a good representation of the global and local responses, and you will be able to do all sorts of scenarios with different defects, different severity of the defects, and different location of your structure. The only issue, like I said, if you go back to the earlier conversations that we had, it's not transferable for every single bridge that you have within the network. You can build the models. There are fairly established approaches in model updating, in building these digital representation. It's just the transferability of this logistically very difficult and quite time consuming. Which leads us to the second group of approaches, and that's data-driven approaches. Now, whilst the model-based approaches gives you this physical interpretation of the response of the structure under a whole host of scenarios, there is the issue of the scalability of it. Whereas the data-driven approach wouldn't necessarily offer you a physical interpretation, but would allow you, because of the computational powers that they do have, would allow you processing a large volume of data and a whole host of clustering, classification, regression using those wide range of data in identifying patterns, not only for one asset, multiple assets at the same time. And that's the focus of the work that we have done in this investigation as well, is to exploit the power of the data-driven approach whilst appreciating that they do not have inherently physical interpretation of perhaps engineering concepts. The impact, the manifestation of the defects would not necessarily be seen in the data-driven approaches. However, they would allow us to be able to identify patterns within the data, hence helping us towards a population-based structural health monitoring. Now, you will be pleased that I'm not going to do a lecture on the machine learning, and actually, as a matter of fact, as a disclaimer, by training, I'm a bridge engineer. I do have a relatively solid, I would call, a statistics background with machine learning. I would say I'm actually at the user side of the spectrum. So I use these algorithms, and I do understand the principles of them, but I don't design the architectures, if you like, for those learning algorithms. Just as a common frame of reference, depending on the type of the data that you have, depending on the task that you want to do, there's a whole host of different classes of machine learning algorithms. This is a very crude classifications, if you like, but I thought it actually is useful in putting the justification for the algorithms we've used in this particular way. So you probably are familiar with supervised learning. This is where you have trained and labeled data. Labeled data in the context of the work that we do is, if you've collected the data, you would know that whether that data is corresponding to a healthy bridge or a defective bridge. If it was a defective bridge, what kind of defects and degradations are you talking about? What is the intensity? Where is the location of those defects, right? Now, that's very ideal scenario. Like I said, in practice, this whole concept of labeled data is very hard to come by. There's a whole effort in actually producing good quality labeled data. But if you would have that, it would allow you a good possibilities for classifications. It depends on the quality of the data, of course. But if you were to look into, say, prediction of the remaining life, it would also allow you regression tasks as well. So that's a group of supervised learning. As is the most case for the structural engineering applications, you don't have that many labeled data, which would lead you to second group of the algorithms, where you have unsupervised learning. Here, you don't necessarily care whether the data actually corresponds to healthy or defect. You are interested in anomalies. Say you have collected a time history of data for your bridge, and you're interested in whether there has been any change in the past 10 years, in the past 20 years, in the global response of this structure. And this group of algorithms would allow you to identify those clusters, those, if you like, time spans within which there has been a change noticeable in the global response. Like I said, it's one of the most common approaches used in structural engineering in general, purely because of that element of lack of labeled, good quality data set within our section. There is also growing interest in a new, well, relatively new set of algorithms called self-supervised learning, or they're also known as GANs. So they are quite a generative learning algorithms, and they generate labels. They generate, in fact, new versions of the input files, and based on the rewarding system, they train themselves. I haven't personally seen the application of the self-supervised learning algorithm in structural engineering, but I can foresee the future where this could be potentially game-changing in structural engineering, if you like. There's also the whole host of reinforced learning, which is actually the principle of all the robotics works and the robotics research, which the learning happens by interaction with environment, and you actually maximize the reward system based on those interactions. I won't go into that learning a group of learning, machine learning algorithms. Crudely speaking, if we were to kind of describe a machine learning algorithm, we call, or the architecture, this is a very basic demonstration of it. You would have an input layer. You would have a different type of input that you could have in your input layer. So you could have a vector, you could have an image, you could have a 3D matrix. So it could be a variety of the inputs that you could feed in. And your output very much depends on the type of task you do. So in principle, you would have an input, you would have an output. And the entire learning actually happens in these connections you have between your input layer, your output layer, and a whole bunch of middle layer or hidden layers. Depending on the type and the depth of these hidden layers, you could have shallow networks and deep learning networks. You may say, why would we ever bother with shallow networks when they are typically designed and used for relatively simple or linear problems? The main reason is essentially, whilst they are simple in nature and in architecture, they would reduce the possibility of overfitting. So if you think about the kind of the regression exercises, there is a problem where you would have an overfitted objective function, which may challenge the transferability of the algorithm you have built. The deep learning algorithms, because they're deep, they have a much, much higher likelihood of overfitting, which is why they're not suited for every single task, and they're not suited necessarily for all the structural engineering applications. As it happens, in this work, we have used the deep learning because of their power in identification of really intricate changes in the input data. Now, when we are talking about deep architecture, we're talking about more than 10 layers in your hidden layers, essentially. And there's a whole host of group of deep learning algorithms existing as well. And I won't go into nitty-gritty of those different algorithms. Frankly, even though that these different type of algorithms, different type of architectures are built for different purposes. So, for example, the CNN algorithms, the convolutional neural algorithms are built for image recognition, for object detection. The RNNs are built for regression, the audio input files particularly, or the text file particularly for the RNNs. The GANs are combination. They are they are designed for different purposes, trained for different purposes, but despite that, they are very much transferable to a wide range of applications. Within a structural engineering industry in general, that includes bridges as well, and civil engineering, to the best of my knowledge, it's predominantly been the feed-forward neural simple architectures, convolutional neural networks. I've seen a couple of works on RNN, but I can't say I have seen any work on GANs, which are the generative adversarial networks, or transformer networks to some extent. So the likes of ChatGPT are GANs and transformers, if you like. So like I say, regardless of which type of architecture you use, you can essentially change the input layer, output layer, and make it applicable to the application that you would like to apply this. Now, within the work that we have done in this particular work is we haven't designed a new architecture. What we have done is to exploit the power of existing architecture, which have been trained on thousands and thousands of images. When I say images, we are talking about objects, normal objects, your daily objects, a cup, a chair, a desk. So these algorithms have been trained on thousands of those type of images. They have been perfected to offer a good accuracy in the object detection, but also a really good computational time as well. So you would see a whole host of these out. So this is by no means a comprehensive list of CNN algorithms that exist currently. It's only a demonstration of the different names if you hear them. Now, what I have in this particular graph is an experiment of the application of these, some of the well-known CNN algorithms in industry, and their accuracy or the performance on a set of known images. However, if you take these algorithms and apply it to an entirely different application, their accuracy completely changes. So this very much depends, the performance very much depends on the type of input that you have, the type of task you expect these algorithms to do. So one experiment that I've seen in the literature is the application of a whole host of these algorithms on respiratory systems in medical engineering, where they have fed in all these different X-ray images of lungs to detect whether it represents a healthy lung, a healthy set of lungs, or a COVID-19 set of lungs. And they've actually compared the accuracy, the computational cost of each algorithm, and it's an entirely different landscape you would see in terms of their performance. Within our work, we have in fact tried and tested more than 10 different architecture, and what we have found for the work that we've done is the GoogleNet architecture in particular offers a superior accuracy, but also because of its simplicity, which I will talk about a little bit about the nature of the architecture that GoogleNet does have, it offers also a very, very optimized computational cost as well. Before I talk about GoogleNet in detail, any CNN architecture which have two main components. There is the classifier, which essentially relates the damage detection, damage features or damage induced features, which your labels essentially. And you have the feature extraction. So you could feed in your acceleration signal, you could feed in a form of a 2D signal process version of your signal, so as in an image. And what this feature extractor does, it further analyzes those inputs and optimizes the distinguishing features within your input. And in the classifier, these distinguished features are mapped against your output. The output, whether it's a binary classification, so is it healthy, unhealthy, or a multi-classification, healthy, damaged, but damaged with a particular intensity in the midispan, or damage with a particular intensity in a certain connection. So those are the type of labels that you could have, Okay, now the beauty of the CNN algorithms is that these two elements are optimized and trained at the very same time. So that's the power of the CNN algorithms. You don't do feature extraction, train the feature extraction, perfect the feature extraction, then do the classifier. You do the entire training in one architecture. And that is true for all the CNN algorithms that you could find as a pre-trained algorithms, or even as an algorithm architecture that you would build from scratch. In principle, what you actually have in CNN algorithm is a bunch of filters. What they do, they zoom in and zoom out of your images, of your input data, and identify the patterns within the neighboring pixels. Now, whether it goes into 10 by 10 pixel or perhaps 2 by 2 pixels, that depends on these construction of your convolution layers or convolution filters. It also has these pooling layers, which essentially downsizes your data files, your filtered images, your extracted features. So it's like I say, they're all a bunch of filters, if you like, that you're applying to your input data, you're applying to the data that it is being processed within the feature extraction layers. And if we put all of those bunch of convolution layers and pooling layers, you would have these CNN architecture. Now, what I have here in this diagram is the Google Nets architecture, which is, like I said, a bunch of convolution layer, a bunch of pooling layer. I won't talk about the softmax and the fully connected layers, but those are the critical elements of any architecture. But what I want to highlight that Google Net is a 22-layer deep network. So in the extent of deep learning algorithm, it's not considered too deep, if you like. Yes, of course, it's a deep learning algorithm. It has more than 10, which is the rough approximation of the description of the deep learning algorithms. But the beauty of the architecture is in this nested architecture. So instead of increasing the depth of the architecture, so adding more hidden layers, what they have done is they've added to the width of the structure. So they have networks within networks by adding these extra convolution layer to each layer of their learning depth, each layer of their hidden structure, hidden architecture, which, as it happens, very suitable for the application in drive-by damage identification. So what we've done, we've taken a pre-trained Google Net architecture. We have applied this to the data that we have for instrumented train, and we've done a whole bunch of, if you like, supervised and unsupervised classification. Now, within any architecture, there's a whole host of parameters or hyperparameters that needs to be optimized. Because like I said, Google Net is trained for an entirely different purpose with an entirely different data set. So to apply that, to transfer that learning into structural engineering application with a particular complexity of the drive-by train data, it won't be possible without the optimization of the hyperparameters, without the change of the structure of your input layer. And we've done that through Bayesian optimization. I won't go into the nitty-gritty, but just a little bit of, if you were interested in this topic, I've pushed a reference there. Bayesian updating has the power of kind of saving you to do grid search. So say you had to do a sensitivity analysis of your architecture initial learning rate, and you're looking at anything from 1 in a million to 1 in 1,000. That would be a grid search if you were to split that into grids and to start to analyze the performance of your algorithm for every single possibility. Now, if you consider that your architecture, in fact, has more than 10 hyperparameters that you need to optimize, it's not only the individual parameters that you need to optimize, but it's also the combination. So if you do a grid search, it would be very time consuming. It's very computational heavy to do all that search zone to be able to identify the most optimized architecture and hyperparameters. Whereas Bayesian updating, because it learns from the previous search, it actually focuses your search zone. Hence, computationally saves a lot of time to train the algorithm using the optimization of the hyperparameters within this particular algorithm. So we've applied Bayesian updating. We have the architecture. The base of the architecture is there. We use the Bayesian updating to update the hyperparameters within the architecture. We've also got rid of all the weightings that have been induced in this pre-trained algorithm. So yes, the architecture is the actual architecture of the GoogleNet, but the weightings are gone. The structure of the data is gone because the input that we are feeding is quite different. And the hyperparameters are gone because we've optimized it for the purpose that we want it to do within this work. So as you do, we started with a theoretical experiment. So this is a very typical experiment in drive-by application where you have a 10 degree of freedom train, track, bridge interaction model. So you would have the structural characteristic for your Euler-Bernoulli beam, which actually represents your bridge. You could have the rail irregularities applied, and you would have this sprung mass vehicle protocol, we call it, model where you could play around with the characteristics of the vehicle, but ultimately you are solving a complex set of equation of motion, a coupled equation of motion system to identify, to calculate the acceleration time history on the bogie, which is a sprung mass, if you like. And because it's theoretical, you could actually do a whole bunch of different defect and different damage scenarios. So what we've done is we've looked at change in the flexure rigidity of elements of 50 centimeter from 5% to 50%. You might argue, well, is 50%, 50 centimeter, is that realistic? You would observe that anyway within the visual inspections, and I would agree with you. However, this is not necessarily for those defects that you could see. It's actually for the obscure and hidden defects, but also it offers you a quantifiable measure of the structural response. Whereas when you measure the defects, if you even measure the size of the defect and the 3D representation of that defect, the translation of that to the actual change in the performance indicator, the utilization factor, requires you to build a numerical model, if you like. Whereas within this, you're actually, within this approach, you will be able to identify those changes in the global response using the instrumented vehicle. Anyway, long story short, what we've done is to look at, right, what each of those scenarios mean in terms of the change in the natural frequencies. So you have these 50 centimeters elements, defective 50 centimeters elements in the mid-span, in the quarter span, and three-quarter span, just to see whether the location of the defect would make a difference, which naturally would. And you can see that as you increase the defect intensity, which is actually represented by reduced flexural rigidity, you would have reduction in your fundamental frequency. And of course, the most intense one, where you have 55% reduction in your flexural rigidity in the mid-span, you are seeing the biggest difference in the natural frequency as well. This is the first mode of frequency, not all modes of frequency. It does vary when you're looking at the higher modes of vibration. So this is only for us to understand what the implication of this particular defect scenarios are in the physical meaning, but we haven't used that for training the algorithm, if you like. So what we've done next, you have the simulated acceleration for all these different scenarios. You add the variation in the speed. So the experiment has been done for 100 kilometers per hour, but actually we have varied the speed with the average of 100 kilometers per hour with the standard deviation of 10%. And we've also looked into not only using the vector of the acceleration, but actually translating that 1D input into a 2D image, because that's where the power of the CNN algorithms lie, its capability to look into the 2D data. Now, translating your 1D data input to 2D images, if you like, could be done through a whole host of signal processing. So there is if you like, a initial feature extraction as your input, if you like. And we've done a whole host of experiments, what actually works for drive-by data, what doesn't. One of the most common approaches and one of the most powerful inputs that you could have is the continuous wavelet transform, because what it does, it gives you the time frequency content of the signal. So it's very rich in information that it could possibly offer. So we create these CWT images for all the scenarios that we have created, for all the different speeds, for all the different ray irregularities, for all the different defect scenarios, and we feed that into the algorithm. Now, in any algorithm, you would keep a set of data for training, you would keep a set of data for validation, you would keep a set of data for testing. Testing and validation are used often interchangeably, but in nature they are different. The validation is often used after each round of training just to see how the architecture is performing, but it's the set of data that the algorithm has already seen it. Whereas the testing is actually on the set of the data that the algorithm has not seen it before. So essentially, it's a blind test on the set of data that the algorithm had no visibility over. It's a really good indication to what extent the algorithm is performing and to what extent it's actually doing an overfitting. So we do feed in these images to the algorithm, we train it, and then we test it. But not only that, one of the challenges you do have with the machine learning application is it's essentially a black box. So it is important that you interrogate each layer of your learning and to see how is the algorithm making the decision and whether those decisions actually tally or are they aligned with your physical principles. So we've done that as well. So whilst we're training, we pull each layer and we look at how the algorithm is making the decision, what part of the CWT, what part of the frequency bands, what part of the time band is the algorithm highlighting as the indicator of the defect, if you like. And we've achieved really high accuracy for any natural frequency change more than 35%. So naturally, as you increase the manifestation of this defect, as you increase the intensity, it becomes easier to detect that in your signals. But the beauty of this algorithm is that it really does not rely on the speed of your vehicle. So we vary the speed, anything from 70 kilometers per hour to 140. The accuracy very much depends on the number of data the algorithm has seen and not necessarily how long is your signal. So it's really powerful in, if you like, in principle, the operational based application. So moving on to the next layer of the investigation, we did a scaled experiment. So we had an instrumented 66 locomotive running over a 25-meter U-shaped beam. So we do actually have this. If you are in the UK, in Guildford, definitely visit Guildford Model Engineering Society. They do have this amazing model network, rail and amazing steam trains. Anyway, that's beside the point. Sorry, I got sidetracked. So we instrumented this train, and of course, we didn't want to damage their model bridges. And what we did, we added masses in different parts of this beam. So we added mass, extra mass in the midspan, we added extra mass closer to the support, and we also changed the intensity of these mass. And we ran this train over the bridge for 2 miles per hour, 4 miles per hour, 8 miles per hour. So we changed the speed. 8 miles per hour was the maximum speed we could have. We also didn't, if you like, record when the train enters the bridge, because that's one of the challenges. Often you don't know, because the GPS timestamps are not as accurate to give you the exact entry point to your bridge. So you don't know where to cut your acceleration measurements and how do you label that based on the state of the bridge. So to be able to kind of experiment with that, whether the algorithm is capable of detecting changes without having to do anything beyond the initial feature extraction, we didn't record when the train actually enters the bridge. So in this experiment, like I said, you measure a whole host of acceleration via the accelerometers instrumented on the train. And when you compare them visually, you cannot see any differences in the amplitude, if you like, or even in the power spectrum and the frequency content of the signal. So visually, it's not necessarily easy to distinguish which one is the healthy one, which one was the changed one. Even when you do the persistent spectrum, where you're actually looking at the likelihood of each of those frequency contents within your signal, you won't be able to see a noticeable difference from one case to even your most intense case. Again, we feed in the CWT images to the algorithm, we train the algorithm, and it is capable of achieving 100% accuracy despite the complexity of the algorithm under completely different environment, under completely different operational conditions. So the speed is changing, the temperature is varied, because we've done this runs in different days. And we've also haven't recorded exactly when the train is entering. There is a variation in the speed itself. It's not a constant speed. So again, the algorithm is capable of identifying not only that there is a change in the global response, it's capable of quantifying that and also localizing it because it's capable actually identifying which one is which. It can label it based on the local intensity and the location. And in fact, it's again highlighting, it's deciding based on the correct frequency bands as you would expect in this particular experiment. But all of that is, if you like, it's an ideal situation, because what you do is you have the knowledge and visibility over every single parameter that could possibly influence the accuracy of your algorithm. So in the final experiment that I wanted to share with you, all of that idealization have gone. So what we have here is measurements on the train, but A, we don't know the characteristics of that train. So we don't know the exact mass, we don't know the exact damping or the sprung mass of the entire locomotive. We don't have a huge volume of the data either. So for example, for that one particular bridge that we've done a feasibility investigation, we only have 5 days of measurements. And for that particular bridge, because it has 4 different tracks, these 5 days of measurements have not been done on the same tracks. So they may include a couple of runs, but they are in different tracks, different direction. Not only that, it's with the operational speed. So we're looking at over 70 kilometers per hour, really, really short signals. And we don't know what they correspond to, when they enter the bridge, whether their speed over the bridge was constant, because that's also a factor in your training. So what we've done, we've started looking at, right, these 5 days of measurements, where do they sit within the cycle of the inspection, the visual inspections, and have done a whole host of review of those inspection reports to be able to identify whether there is a particular defect that we can associate that with a change in the global response that can be detected via these measurements on this instrumented train. So that's what you see. So you have 5 days of measurements span over 3 years, and then you have inspection reports done not necessarily on the same day. It might have been a month before, it might have been a couple of months before, it might have been a year after. So there is this time lag between what you may use as your label proxy and your actual data that you have collected. So like I say, there's a whole host of challenges associated with this. We also have no visibility over the state of the wheel condition or the rail irregularity. In fact, the measurement trains are used for the rail irregularities, but those profiles were not known at the time of this investigation. So again, did a similar experiment. We built these CWT images for all these 5 runs for all these different tracks, and we feed that in the algorithm. I'll come back to this slide in a minute. We also needed to build additional damage scenarios because the defect scenarios that we had with this case, it was very limited. So we wanted to know and investigate the power of the algorithm if you were to have different intensity of defects, a different location of the defect. So in parallel to the entire workflow, we also started building these calibrated train track bridge interaction models, which purely is used essentially for generating additional data set, additional label data. But there is a huge work itself involved in the first stage, where you have the NMT measurements, the new measurement train data, and the inspection reports, and trying to tally these, to use these for the labeled data sets that you need to create for your algorithm, essentially. This is an ongoing investigation. So far, what the algorithm has been able to do is to classify the data into the year in which they have been collected. Now, the power of this is that we can actually start building the defect degradation profiles for the entire structure. It's also capable of identifying 2 separate clusters within which we actually have a distinguishing scar occurring in one of the piers of the structure. So it has allowed us to identify when that scar has actually manifested in a sort of a response that needs to be detected or can be detected via this measurement train. Now, this is very important. The scar might have been there much longer. It's just the intensity has now reached to a point that the train measurements is capable of picking that up within the data that it is available. And we are now in the process of actually generating this whole host of new scenarios that we are currently using to train this algorithm further for a wider range of damage scenarios, but also increasing the transferability, the scalability potential of the algorithm for similar type of bridges on the network. So what's next? We now have about 100 miles of train measurements, which we are experimenting on a population-based investigations for a cohort of metallic bridges, purely because we have more visibility over the type of defects that we have and the type of global responses that we could expect for those bridges. We also have a new set of measurements on a different side of the network, with a higher resolution of accelerometers, which would allow us to compare different settings for a different type of resolutions for the measurements that we have for that cohort of bridges, and see whether the different measurement system could actually offer something better, or we are better off having a longer period, more runs over a certain bridge rather than a more resolution on a certain bridge. That's all there is. I'm going to stop there. Hopefully I haven't stunned you all to silence. I've put my email address there. Hopefully you found this of some interest, at least some part of the presentation, if not all.
Well, thank you very much, Donia, for the webinar. We'll now move on the question and answer session. I don't know if does anyone have any question. Yeah, there is one. Samrul Hoda.
Thank you, Professor Dorna, for such a wonderful presentation. Professor, I have a couple of questions. First is how you are getting the location of damage.
Thank you for that. I will correct you. I'm not a professor yet, so don't able to. So all the data that we have collected, they are timestamp and geostamp. So we know roughly where they are at. So it does allow us to know approximate location, but what you have in these measurements on the new measurement train, it's not one single event. So it runs, say, for 10 miles of track. We have then narrowed down where the location of the bridge is, And within that approximate location, we've added about 2 miles on each side to ensure that we've actually captured the entire run over the bridge, but part of the track as well. Okay, but they're all georeferenced anyway. Even if not accurate, that does help us in approximate location of the signals corresponding to the bridges.
Okay, got it. This algorithm is doing it is segmenting the overall bridge into the part, and it is giving us a approximate location.
They're all georeferenced. So the entire train actually has a GPS. It's not a very accurate GPS, but it is all georeferenced.
Thank you. And my second question is on slide number 22. You have shown that the accuracy of the ML model. So there for the higher level of damage, like 60% damage, accuracy was around 50% or 60%. So, ma'am, how much we can rely on this type of model, as 60% is higher level of damage, still we have accuracy on only 60% or 70%. Still we have 30%.
Let me bring that a slide so that I ensure that I'm showing the correct one and I understood correctly. Hang on a second. Sure. This one. Okay. Is this the slide you're referring to?
Yes, ma'am, this slide.
Okay. So the accuracy for 55% is, the accuracy for the 55% is actually close to 100%. So the bars are representing the accuracy, the lines are representing the change in natural frequency. So for the 55%, regardless of whether it's quarter span or mid span, it's actually 100%. It's close to 100%. I think it's 99% something. Then same goes for 45%, very close, so over 90% accuracy. For 35% change in the flexural rigidity, again, you are achieving really good accuracy. But as it goes to 25% or 15% change in the flexural rigidity, you have to bear in mind it's very small. It's 50 centimeters element anyway. You are then looking at 80%. But again, it's a theoretical investigation anyway. But there is limitation. So you cannot, I would not believe that this is capable of detecting local defects. So the likes of fatigue cracks, for example, will not be detectable with this approach. But any defect that would manifest in the global response with a certain intensity, now what that intensity is would change from one group of bridge to another group. I would even hazard a guess within one group of bridge would be quite varied.
Thank you, Ronna.
Pleasure.
Well, there is another question here. I have one question. How expensive was the project?
How expensive was
the project?
Oh, okay. You'd be surprised to hear it wasn't that expensive. So this is essentially part of the work that I did for Department for Transport, the feasibility investigation. And because we were able to demonstrate that it is theoretically and practice-based, it is feasible. We've been given the data for free. So Network Rail have been very kind and generous in sharing that additional data with us. And we are now in the process of actually recruiting someone to be able to spend a little bit more time on this additional data to do the experimentation on the population-based monitoring. So overall, perhaps something close to 150K, which in the context of the projects, it's not that expensive.
Okay, great, thank you. The last question, it says, thank you for the great presentation. Will you please describe how did you define damage scenarios from 5 to 55?
Right, okay, so imagine that you have a 15-meter Euler Bernoulli beam. You discretize it into elements of 50 centimeters, and you change the flexural rigidity. So Young's modulus times the second moment of area in the simplest form for each of those elements. Then you reduce the flexural rigidity from 5% to 55%. That's exactly what we've done here. But that answers your question.
I think that yes, I would like to take a group photo, so please don't disconnect. But before doing that, well, thank you all for being here today and for your participation. We are especially grateful to our speaker, Donia, for, well, I met her at the University of Surrey, and we want to start this type of collaboration, not just with the webinar, with other type of research as well. And your expertise and perspective have enriched our understanding, and we appreciate the time and effort that you have invested in this presentation. So we hope that to have the pleasure of welcoming you in person here in Ecuador in the near future, hopefully. So your presence will be as when we started at this, well, the weather is a little bit different from Surrey, but it is fine. So your presence will be a really great opportunity for us to collaborate and learn from your expertise. No?
Absolute pleasure. Thank you.
Thank you. And now I would like to everyone to turn on the camera so we can take a picture. So I think that we are ready. We will start. Well, Juan Pablo and me, we will take some pictures just in case there is something. Okay, I think that we are ready, no?
We say cheese.
Yes, I already take the pictures.
Okay. Yeah, I think that we have the picture. So, well,
Yeah,
great. Thank you. Thank you to everyone. And I hope that we can see you in the next webinar that we will be presenting. No? Thank you
Thank you very much, Nasi, and everyone for listening. Have a lovely evening or day.
Yeah. Thank you.
Bye.
See you. Take care. Bye-bye.
Recording stopped.